Hi everyone, this is a video about vector spaces, and in it we're going to present two simple but interesting examples of how to calculate the basis and dimension of a subspace that's given by its Cartesian equation. Let's discover the maths. We're going to calculate the bases and dimensions of the subspaces S and T shown here. Let's start with S. We know that the vectors of S are those whose components satisfy the equation z equals 0. So our system of equations is a single equation that involves just z. But we still have to consider all the unknowns, x, y and z, even though some of them don't appear in the equations. Since we have only one equation, we don't need to use the Gaussian method to reduce the equations. We have that the number of parameters equals the number of unknowns minus the number of equations. In this case, the number of unknowns is 3 minus the number of equations, 1, so that we have 2 parameters. Let's now assign these parameters. As you know, the appropriate thing, whenever possible, is to assign the parameters from the end to the beginning. So we'll start with z. But of course z is always 0, whereas a parameter is variable. Therefore we can't assign a parameter to z, and we have that y is equal to alpha and x is beta. Now, if x, y, z is a vector of S, its components are solutions of the system, so they satisfy this. In parametric form, x, y, z becomes beta, alpha, 0. Now we separate this sum of vectors so that each of the vectors has a parameter. So we have beta, 0, 0 plus 0, alpha, 0, and then we take out beta and alpha to give beta times 1, 0, 0 plus alpha times 0, 1, 0. Notice that every vector of S is a linear combination of 1, 0, 0, 0, 1, 0. S is generated by these vectors, and therefore the set formed by these vectors is a generator system. Also, since the vectors are clearly not proportional, they're linearly independent. We have two linearly independent vectors that generate S. So the set formed by them is a basis of S. Since this basis has two vectors, we have that all the bases of S will have two vectors, so that the dimension of S is 2. Now we'll calculate the basis and dimension of T. The vectors of T are those whose components satisfy y minus 2z equals 0. Again, we have a system of equations with a single equation, but don't forget that the unknowns are the ones that appear here. Again, since we've got only one equation, we don't need to use the Gaussian method to do a reduction. The number of parameters equals the number of unknowns minus the number of equations. Here the number of unknowns is 3 minus the number of equations, 1. So we have 2 parameters which we'll now assign. Again, we start at the end. Z equals alpha, y equals beta. We're just missing x, which we have to express in terms of the parameters. But notice that we don't have any equation where x appears. This means the parameter assignment doesn't work. So what do? Well, keep trying. Let's keep z equal to alpha, and instead of y being beta, let's make x equal to beta. Now y is missing, but notice that y does appear in the equation. So we substitute here y minus 2 times z, which is alpha, equals 0. So y equals 2 alpha. Now we have all the unknowns based on the parameters, and we can continue. If x, y, z is a vector of t, its components are solutions of the system, so they satisfy this. In parametric form, x, y, z becomes beta 2 alpha, alpha. Then we separate this into a sum of vectors, so there's just one parameter in each. And so we have beta 0, 0 plus 0, 2 alpha, alpha. Taking beta and alpha out, this becomes beta times 1, 0, 0 plus alpha times 0, 2, 1. Notice that every vector of t is a linear combination of these vectors. So t is generated by these, and therefore 1, 0, 0 and 0, 2, 1 is a generator system of t. Since the vectors are clearly not proportional, they're linearly independent, and so constitute a basis of t. As this basis has two vectors, the dimension of t is 2. With that, we've calculated everything we need to, and we've finished the exercise. I hope you found this useful. Please subscribe to the channel if you haven't already, and I'll see you again very soon to discover more maths.